All right, let's take a look at the homework for section 3.3, working with complex numbers. Number one, we have the square root of negative 361. Of course, we cannot take the square root of a negative, so that moves out as I. So we really have I times the square root of 361. If you try to look for a factor tree here, it might be difficult, but just put it in the calculator. What is the square root of 361? And we can see, if we put it in the calculator, that it's 19. So this is a perfect square. You might get a large number that you might not recognize as a perfect square, but sometimes they can be. Like 14 squared is 196. 17 squared is 289. So it might just be an unfamiliar perfect square. So the square root of 361 is 19. So this is 19 times I. And we can just write it like that. Number 2 is not a perfect square. Again, we take this negative, move it out of the radical as I. And then we can do a factor tree for 50. We know it's even, so divide by 2 to get 25. We cannot break down 2, but 25 is 5 times 5. So if it pairs up, we write one of them outside of the radical. We bring in our I that we pulled out, and then the 2 stays under the radical. So again, if you struggle with simplifying radicals, I have videos that look at several examples of just that, if you want more help there. Or perhaps you think about the square root of 50 as the biggest perfect square factor, which is 25. Square root of 25 times the square root of 2. This will lead nicely into the next two problems. That's the square root of 50. That's not what I meant to do, though. The square root of 25 is 5, and then root 2. So I multiplied those because look at number 3. When we have two radicals being multiplied, we multiply the two radicands, what we see under the radical. Now you might be tempted to say that this is a positive 36, because negative 9 times negative 4 is a positive 36. But there's no such thing as the square root of negative 9 or negative 4, because we are in the land of imaginary numbers. So if we pull out I, we have I root 9 times I root 4. Now, if you don't already know this, it's important to understand that I squared is negative 1. Because when we have a factor of negative 1 under a radical, we know that we pull it out as I. So if we squared both sides, we would have I squared equals negative 1. So here, 9 is a perfect square, so is 4. So the square root of 9 is 3. So this is like 3i times. The square root of 4 is 2. So that would be 2i. And 3i times 2i is 6i squared. And I squared is -1. So this is like 6 times -1, meaning our answer is -6. So here, they were both perfect squares. Once we pulled out I, the radicals went away entirely. Just became the square root of 9 was 3. The square root of 4 is 2. Here, these are not perfect squares. Again, you might see it in ALEKS with the two radicals just next to each other, which means that they're being multiplied. We can put a little multiplication dot to show that it's being multiplied. So again, we pulled out the negative as I. I times I is I squared. And when I multiply two radicals, if they have the same index, like two square roots, we can multiply those. And 15 times 5 is 75. Again, we know that I squared is -1, so this is really like a -1 times the square root of 75. If you said -75, you would get the answer marked wrong, or -√75, because we can simplify the square root of 75. So that's like 25 times 3. 25 is 5 times 5. These are all prime numbers. So this is our factor tree. So again, think about what we already have. We have a -1 out front times, we move one of these 5s out. It is no longer under the radical of the square root of 75. What's left under the radical is that lone 3. So the I times I will just make the coefficient negative. So we have -1 times 5, or I'll go over here, -5√3 would be our answer. Two more problems in this section. Number 6 is a kind of an interesting one. Students will probably think they need to do too much on it. We can simplify the square root of -20. We know that it's I root 20. And then you could factor tree this, or maybe you think about it like this. The square root of 4 times the square root of 5. The square root of 4 is 2. So this is 2i with root 5 left under the radical. And then this carries down. And that's all we do. All we could really do was simplify the radical. These are not like terms, certainly, so these don't combine. So this is as far as we go. Stop there. And then number 7. 7's a good one. When we have a binomial, or any polynomial, in the numerator of a fraction, we can break up or split up the fraction. And it is not considered in simplified terms if part of your fraction will simplify. Just a quick aside here. If I had something like 17 plus or minus 3i over 22, 17 is a prime number. It's not going to be divisible by 22, no shared factors. 3 and 22 would have no shared factors. we could stop there, and you'll get some answers, with radicals as you solve using the quadratic formula that kind of just look like that. But if it does simplify, like 8 and 22 have a shared factor of 2. So in order to get this problem right, we need to simplify it. So I have 8 over 22, because both terms in the numerator are being divided by 22. And then I also have 13i over 22. So this piece right here will simplify, but this will not. 13 is a prime number. 13 and 22 have no common factors. But here, 8 and 22, we can divide both by 2, or put 8 over 22 in the calculator and hit math, enter, enter, and you will get 4/11 plus the 13i over 22. And we cannot combine those. That's as much as we can do. So we just split the fraction. Each part of the numerator is being divided by 22. If it were a minus, we would just change it to a minus sign. And if you can, simplify, and then you're done. So there's 3.3, and I hope that helps.